Manufacturing modern electric vehicle batteries requires joining pure aluminum directly to nickel-plated 304 stainless steel. The standard method for securing these thin-sheet battery tab connections is continuous laser welding. The primary engineering constraint in this process is spatter. When molten metal ejects from the weld pool, it causes localized material loss and leaves conductive debris on the surface. In a high-density battery pack, this physical degradation translates directly to increased electrical resistance and compromised overall efficiency. This diagram outlines the standard geometry of the experimental welding path designed to test this problem. The laser travels along a highly precise, symmetrical sequence, forming a 2.5 mm outer circular boundary before executing a tightly spaced 0.1 mm zigzag hatching pattern across the interior. But this macroscopic scanning electron microscope image reveals a strict discrepancy between the intended symmetry of the laser path and the physical reality of the final weld. The spatial distribution of the defect field is entirely asymmetrical. The left boundary of the weld zone is heavily polluted with solidified spatter, while the right side remains relatively clear. A second anomaly appears on the vertical axis. The top edge of the circular boundary exhibits a much higher density of ejected material than the bottom edge. These localized clusters identify spatter as a deterministic outcome of fluid dynamics. By isolating the directional mechanics of the laser beam, we can reverse engineer these spatial anomalies and systemically eliminate the defects. Resolving the horizontal divide between the left and right boundaries requires mapping the exact physical forces operating inside the microscopic melt pool. When the 1064 nanometer laser strikes the surface, it forces the metal beyond its melting phase, straight into vaporization. This phase change generates a localized pocket of expanding gas, creating extreme recoil pressure driving down into the cavity. That pressure triggers a specific cycle of fluid dynamics. The liquefied material is forced to slide down the front wall of the keyhole, where the recoil pressure then catches it and accelerates it rapidly up the inclined rear wall, working directly against gravity. As that fluid reaches the top surface, the pool's surface tension is the only force holding it in place. When the upward momentum of the molten metal exceeds that tension threshold, a droplet breaks free. Because it is riding up the rear wall, it ejects backward, flying exactly opposite to the beam's forward trajectory. This microscopic backward ejection vector explains the macroscopic zigzag pattern. As the primary hatching lines travel horizontally from left to right, the internal keyhole pressure consistently shoots the molten spatter backward, causing it to accumulate heavily along the left boundary. This schematic maps exact starting and ending coordinates along the perimeter of the weld path. Measurements in the corresponding bar chart confirm the physics. The total spatter area at the starting coordinates is consistently larger than at the ending coordinates. The physical geometry of the keyhole forces recoil pressure to exhaust backward. The beam's programmed trajectory directly dictates the x-axis defect distribution. The mechanics of backward ejection solve the horizontal axis, but they do not explain the vertical spatial anomaly. The beam mechanics at the top and bottom of the weld are identical, yet the top boundary suffers a much higher defect density. The difference lies in the chronological sequence of the operation. The programmed welding path initiates at the bottom region and incrementally zigzags its way up, terminating at the top. This sequence introduces the temporal variable of localized preheating. As the laser continuously fires, the surrounding metal acts as a sink, absorbing significant thermal energy ahead of the laser's physical arrival at the upper boundary. By the time the beam reaches the top region, the material is already at an elevated temperature. In fluid thermodynamics, a melt pool's surface tension shares an inverse relationship with its temperature. With the top region preheated, degraded surface tension offers far less physical resistance against internal recoil pressure. The mechanical threshold for droplet ejection is lowered. This plot measures spatter area against laser power for all four boundaries. The green trend line representing the top boundary sits consistently higher than the black trend line representing the bottom boundary across every single power level tested. Cumulative thermal preheating progressively compromises fluid retention. The final stages of a continuous weld are structurally more vulnerable to high-volume defects than the initial stages. Visual observation confirms the mechanics of spatter generation, but qualitative analysis is insufficient for industrial process optimization. To eliminate the defects, the physical phenomena on the surface must be translated into a rigorous, quantifiable data matrix. This side-by-side comparison shows the digital processing methodology. The original grayscale image is stripped of its background. An algorithmic threshold converts it into a binary matrix, rendering ejected material pure white against a black void to extract exact micrometer area values. With the defect footprint digitized, it can be tested against the two primary operational inputs. The first is laser power, which has a direct correlation to the intensity of metal vaporization inside the keyhole. Plotting the extracted data reveals a severe exponential correlation. As laser power scales from 10 watts to 20 watts, the heavier vaporization drives up internal recoil pressure, drastically inflating the total square area of the resulting spatter field. The second input variable is welding speed, which maintains a strict inverse relationship to localized heat input time. Increasing the travel speed limits the amount of time the laser dwells on any specific coordinate. This shorter exposure restricts thermal saturation, which preserves the material's surface tension and naturally stabilizes the melt pool against ejection. By utilizing binary thresholding, chaotic microscopic ejections are successfully converted into a precise mathematical matrix governed entirely by power and speed. Because surface tension and recoil pressure shift dynamically throughout the weld, the interaction between laser power, travel speed, and spatter generation is strictly nonlinear. Finding the exact point of balance requires an advanced mathematical model. The data enters a second-order polynomial regression model. This algorithm calculates the exact relationship between power, speed, and final spatter area. The R-squared values range between 0.88 and 0.92, verifying the model's high fidelity to the physical surface. With the geometry mapped, numerical optimization, specifically Newton's method, is applied to navigate these quadratic equations. The algorithm establishes a second-order approximation to locate the absolute minimum possible spatter area within the operational range. The regression model yields definitive engineering parameters. To suppress recoil pressure and preserve surface tension, it requires low laser power paired with high travel speed. The physical difference is immediate. An unoptimized process produces a violent ejection field, but mathematically optimized parameters lock fluid dynamics in place, yielding a stable, clean weld pool. Spatter in electric vehicle battery manufacturing is not an inevitable mechanical failure. By mapping keyhole fluid dynamics, measuring thermal degradation, and applying parametric control, defect elimination becomes a strictly mathematical problem with a definitive engineering solution.